My name is Seda. I'm with Geocom. I'm one of the project managers dealing with geotechnical projects, part of Geocom Consulting Group. What I will be talking about today is kind of challenges that we face with subsurface characterization and in geotechnical engineering. So I just want to start with a question that the title speaks to itself, that what we see most of, what is the most what's the most, what do most geotechnical projects have in common? So I guess what I want to make a point here is, as the title speaks to it, that the subsurface characterization is one of the challenging parts of the project. Even though we do very complicated finite element models or any kind of stability analysis or calculations, most of the time we spend a lot of time really characterizing the materials that we're dealing with and making sure we represent those properly in our models. So that's what I will be kind of touching today in general. What typical problems that we can be dealing with, deep excavations, we might be dealing with the soil behavior with and without water that we need to understand and manage the water within the soil and making sure we properly model that in our analysis of deep excavations. It could be dealing with a slope stability problem where we determine where the loose material is. This could be waste material that are retaining or any kind of other slope stability problems that are not natural slopes that could be also governed by some soft material. We could be dealing with a liquefaction problem during earthquakes, where most of the saturated sands, not only the sands, I guess I should have put here sand-like soils, so not only sand, silts, or any kind of waste material that are non-plastic are susceptible to liquefaction. So we could be dealing with materials like that as well and trying to solve liquefaction problems. And other examples could be offshore wind problems, not problems with design, as well, that you have soils with under unique loading conditions that are not very typical to our typical geotechnical projects. So that's, again, another unique situation that we might be facing. So with that introduction, I think I just want to give you a brief introduction, outline what I'm going to talk about today. Is I'll give a brief introduction where what are the key considerations that I think is good in preparing in subsurface investigation, which we don't all field, and I'll touch on some of the field investigations, not all, and some laboratory investigation, and mostly the site characterization with the combination of these two, and what are the key points, what to look for, and some examples from case studies, and we'll finish up with the key takeaways. With that, let me give a brief intro about what I think are some key considerations in determining the subsurface characterization planning for a subsurface investigation. Of course, the goal of the project, like we touched on a few slides in the beginning, what's the problem? Are you dealing with a problem and assessing in a situation, or are you designing to a certain project with unique loading conditions or unique materials? You know that unique materials exist part of your project. So your project goals, of course, is the most important because are we doing a seismic assessment, a static assessment, that will all play into the project goal. That ties you to the loading conditions that I called it as, probably I should have said short-term and long-term loading conditions or seismic type of loading conditions here. But what I mean by drained and undrained is, I guess, under those loading conditions, how do you expect those materials are going to behave? And which would determine the selection of your properties, or even before planning for your subsurface investigation, because you want to target to sample the key materials based on these loading conditions. And geology of the site and the historical information about the subsurface materials is always is a go-to in the beginning when you're planning. Is I guess the value of that cannot be stressed enough, especially the geologic information, which would tell you about how the materials are deposited. And historical information about these materials can give you some clues where to really what to look for, again, depending on what the goal of the project is. And with that, you prepare your investigation targeting these materials, which I call them key materials for that particular project. And if you want to capture a unique behavior, if you think a unique material is going to govern the assessment, then you target those to be sampled and interpreted. With that, let's start with some of the field investigation that could come into play here. I'm not going to touch on every single lab field investigation. I kind of highlighted some of them that I will be including in this presentation, which includes drilling and sampling, as we typically do, and then standard penetration tests. I'll touch these two together. It's kind of drilling and the standard penetration test in one place, in one tent. Then penetration tests, which are more widespread these days because of their value in interpretation of these soil behaviors, and then some geophysical tests that could give us some stiffness parameters for the materials. Again, if you're dealing with a seismic assessment, which can be very crucial information for your interpretation. And again, all the purpose of this investigations field and lab is to understand how these soils behave and basically assign the right engineering parameters for your assessments or designs or for your numerical modeling. Any type of tool that you will be further using to understand the soil's behavior. Starting with briefly, I'll keep this part very brief. I'll try to do that. I'm just trying to set the stage for the later on examples. But what I will be kind of talking here is briefly what standard penetration test is. It's one of the most widely used field tests that we have. And what it does is using a standard hammer, dropping it from a standard height, looking at the penetration, and collect the number of blows for a certain penetration. And you're seeing a sketch of that here, prepared by a domain here, which is kind of nice, showing how the drops in penetration is valued. This is typically showing, these are in meters, but what we have is in 6 inches in increments. Typical to 18 inches can go up to 24 inches depending on the project. I have a little video here to show you, which is using an automatic hammer. And if you pay attention to the rod here, which is going to penetrate, and you see the white marks that are the 6-inch penetration marks, you can kind of see how SVT's SVT blow counts are collected. So I'm going to click here and pause for 18 seconds. You see these white marks for 6 inches penetration is basically standard height penetration, and it's being recorded to prepare a boring log that we use in our first understanding of what the material that we're dealing with, and basically collect and index data to understand what's the material below. We have the chance of sampling it, also getting an understanding of its density through the number of blow counts. So that's the SPTN values are typically what the number of blow counts are called. But what's very key to this standard penetration test is basically the calibration of this of the hammer, which needs to be standardized, and the energy transfer ratio, which is the one of the most important corrections for this field data, and needs to be really done properly, because it would have a real impact on the number of blow counts that are collected. So And this ETR should be maintained and obtained on each rig at least once in 12 months. And this is one of the most important things about the SPT block counts, and later on will be used as an interpretation of many soil parameters. One of the drawbacks of this SPT is this, you have to have gaps between, you have to have enough distance between the two block counts collections, and that can cause interruption and can lead to some missing strata information. But at the end of the day, SPTN values are very typically used. That you collect them in a boring log, and it usually gives you a good understanding of a good starting understanding of what you're dealing with. It also this drilling activities will give you the opportunity to do sampling. And split spoon sampling is most widely used to get a disturbed material, but it will allow you to get the material visually, classify them, and you're seeing a split spoons and with some bottom ash material here on the left. And you can also use tin walled samples, which are attempting to get so-called undisturbed samples, but relatively minimally disturbed samples, where you can use Shelby tubes or a piston sampler, which one of them you're seeing on the right here. So these help you to collect the critical materials that you're trying to characterize. And having a borehole, you can use the opportunity to install instruments to understand the water behavior, and you can also install other instruments if your project calls for it, and if you think the monitoring is crucial to your project. With that, I'm just going to touch on compenetration test, which where compenetration test has been much more widely used recently, more widespread than before, which because it's relatively fast and provides a good quality data as in a profile. So it's more of a continuous profile of a data, which is different than the SPT data. And where you can really you can add modules to this to this testing. Typically what it does is with the tip resistance and the sleeve resistance, you have an understanding of the behavior. That's very typical to a cone. But you can also add the pore pressure measurements. You can also add shear wave velocity measurements, where you can understand the stiffness properties or the density of your material, which is it could be very important to depending on again the project needs. So, but the most I find the most important value of this testing is the continuous data, which tells you about the variability within a certain soil layers. Here's a typical CPT result where you see that tip resistance that I just talked about tells you the variability and the differences in the layers. You see the skin friction talks about the cohesiveness of the material, and you see the pore pressure data here, which also tells you about how that this is an important and a crucial information about. Yes, the CPT push rate matters, and it is sort of a that could be, you could use the standard rate, or depending on the material type that you're dealing with or the loading conditions that you want to create, you can choose to do a different rate, but it gives an idea about how permeable the layers are, how it's going to behave, if pore pressures are going to build up, what type of pore pressure behavior is dominating. And you can also measure the shear wave velocity, like here on the right. And this draft data, this draft CPT data is with this with the vendors these days. You can quickly get at the field these draft data, and it could be very beneficial to take a quick look at it to see a general idea, to get a general idea of the delineation between the soil layers. And that's why which I will kind of tie this in a few slides, that doing a companion CPT with a boring can be very helpful. And if you're trying to make an efficient number of borings and number of CPTs for your project, you can use the benefit of the draft data to kind of plan your sampling and your split spoon and SPT block. So you can choose to do that. I'll touch on this in a few slides down with the value of the combination of the two tests. CPT, not only that, there are a lot of correlations right now out in the literature. It's good sources where mostly led by Robertson, and you can correlate these data to any kind of parameter that you're going to need in your project. Could be undrain strength, it could be a friction angle, it could be in 60 values too, corresponding in 60 values. So you can use these interpretations that are readily available, but it requires caution because all these relationships have certain assumptions, and you really need to make sure what you want to do with this data. So you can use the benefit of readily available process data that are given by the vendors, but you can choose to process your own data depending on the need. And some geophysical tests that I want to touch on: shear wave velocity measurements, seismic wave measurements are important. They give an understanding of, especially in the area of liquefaction, or you're dealing with a seismic assessment where you need the site response. The small strain shear modulus, if it's part of the material, one of the material properties that you're looking for. Measuring shear wave velocity is key. Not only that, it can also help with the delineation of some of these layers, soft layers that you're looking. And there are many ways of doing it these days. So they kind of have two major differences. One is being active seismic, and the other one is passive seismic. Active seismic is more common, which is most widely known as MASW, cross-hole seismic or downhole seismic, where you can measure the shear wave velocity. And passive seismic, mostly this is more of a newer technology where you can use the basically ambient vibrations to calculate these differences in shear wave velocity. The benefit of that is it has the luxury of giving you a 2D scan. It's more of a mapping, and you have the benefit of here's an image from an S scan. You have the benefit of kind of pinpointing where the soft layers are compared to the other layers surrounding it. And this can become very crucial in a liquefaction example. We usually, if you were to have a borehole here and thinking that this is a soft layer, if you know if it is extending to what's the extent of this soft layer, if it is only local to that area, you are limited to your CPT pushes or your boring locations, which you're kind of choosing, sort of educated, but again, you're limited to a certain extent. So these type of scannings and new technology can be handy in terms of characterizing the soft materials. So one of the examples of a good practice is with drilling. As I said, as we all know, SPTN values are very widely used and correlated to many parameters that we use in our models in our practice. So, and the drilling activity can have some impact on the collected data. And we already talked about the hammer efficiency that could really affect not knowing the true efficiency of your hammer and not correcting for that properly can have a big impact on the SPT block counts that are collected. Not only that, I also want to touch here on the drilling techniques quickly. Here you see a slide where you see the block counts on the left from the same material with the hollow stem auger boring, whereas on the right you have a mud rotary boring where the drilling activities were done with different drilling techniques. And you see in the middle is a chart which shows the SPTN values that are collected, and we kind of wanted to show. So here you see the differences between the clay and the sand layer. Spatially, in the granular materials, you see the difference between the two different techniques of the drilling, and how they can play a role in determining the number of block counts. And this is also mentioned that I put some of the two of these good resources here that talks about it. One is Seed's paper about SPT procedures for liquefaction assessment, and Ladd's for soft ground characterization. So not only with the granular soils, the effect of the mud rotary boring and keeping the mud at the top of the borehole, keeping the mud density controlled, can really help with the quality of the samples that you're collecting, and also with the number of SPT block counts that you're going to use in your analysis or in your design down the road. So that's one striking example that I wanted to share, which could be in your control, that you can request that when you're planning for your subsurface investigation. The other one that I touched a little bit earlier is doing a companion CPT and SPT tests and drilling. So this is a good one because as I said, so SPT is good because you have the chance of, and drilling, you have the chance of collecting materials and collecting more data. But CPT is a good indicator of what you're dealing with in terms of changing layers, and if the pore pressure behavior can tell you about where you can really sample materials, because most of the materials that are good for sampling will have a different pore pressure response. So what you're seeing in the slide is a very what you're seeing on the left is the QT resistance. And then here, the pore pressure resistance, where with the blue, we're calling it as a good candidate. Like if you were to push this CPT before your drilling activities, and you have the draft data in your hand to plan for your drilling, and if you go and do your drilling right next to your CPT, which is a good practice to do, then you will have a chance of programming your drilling activities where you want to do the SPT test and where you want to do really the tube sampling. So this is kind of a good one that we find it very beneficial in our projects, that can help us at least a little bit more knowledgeable in collecting data, and reduces the amount of time iterations that you go to the field and collect more data. At the end of the day, when you're down to really coming up with parameters, you have more information and more kind of information to compare against to get a better picture of the materials. Again, I'm not going to talk about every single lab testing, but I just want to touch on the ones that I typically use. I kind of separated them, kind of put them in headings of 4 by calling them classification, where I mean most of the STS classification tests that are typically done as part of the geotechnical projects if lab testing is enrolled. These are, I'm going to touch on these quickly. I want to really stress the effect of the importance of the X-rays of the tube samples that can help you select your testing for preparing for material properties. Consolidation testing is very important too. Again, it's not only for the settlement type analysis. No, that's kind of go-to for those, but understanding the maximum pass pressure of a material, understanding the stress history of a material can be very important. And strength testing is very widely done. We do direct shear or triaxial testing for friction angles and direct simple and cyclic simple shear. So I'm going to kind of quickly give an example of these. I'll be brief and then be again doing some good practice examples in the following slides. And then the final one, or before I forget, is the stiffness, I call it, but it's basically modulus and damping by resonant column. This is, I know it's not every project has this. It's kind of an advanced test and hard to interpret. But if the project calls for it, like if you have a seismic assessment that you're looking for an amplification of a site, and if it is, especially an amplification of the slope, let's say, where your structure is your earth retaining earth material, basically, that could be very important. So again, depending on the project, the need for these advanced tests are valid, and that their value is cannot be overstated. And laboratory shear wave velocity measurements is also one of those advanced tests. It may not be very easy to do it, but it can give you an idea about the shear wave velocity, which is again a very more widely used these days, an important parameter to understand the density of the material. Also, if you have the field measurements, like with the geophysical tests, and if you do the same in the lab, you have the chance of comparing the two. So without going too much into detail, which probably I will do in these slides as well, let me move on. So with classification, this is very typical. I'm going to keep it quick. It's basically gradation and plasticity of a material where you kind of classify your materials. It's very important, though. You have to start with this and try to, sometimes it can, which I will have in one of the case histories, it can be important. You have to confirm what your material is. So visual classification done in the field needs to be accompanied with the lab classification, where you usually call the materials coarse-grained or fine-grained, and typical these all these abbreviations that we're all familiar as geotechnical engineers, we're familiar with, that can give us a sense of what this material is. And plasticity can be an important tool to kind of gauge where sand-like and clay-like behaviors are if you're really, again, doing some liquefaction type analysis, you have to have an understanding of what you're dealing with. And also it can give you an idea about how heterogeneous your materials you're working with. So you can have situations where you have majority sand-like, but you have some plastic behavior there. So there will be, of course, situations where things are not nice and clean, which we all know. All right, I want to stress not only the USCS, the typical classification. I wanted to mention the specific gravity, especially if you're dealing with unique materials, which you're dealing with like waste materials, mine tailings, or coal ash. They have a very different specific gravity than the typical soils. Typical soils are 2.6 to 2.7, but these materials can be different. And it can be as low as 2, it can be high, and depending on their chemical content, mineral content. So here you're seeing an example of some coal ash material that are really low specific gravities, and this can affect the results of interpreting some results like resonant column tests, or also when processing your CPT data. So those pre-processed data that are supplied by the vendors, or like typical relationships, use some typical values, and you may want to adjust those based on the specific gravity. So it's part of the classification that I wanted to put it out there, since we're talking about unique materials here. Now, last but not the least, for sure, is the X-rays of the tube samples that you're collecting. It is important, and if you're dealing with sensitive materials, and if you know that sample disturbance is always there, and if you're going to rely on your lab testing, it's very important to really know what the tubes are. And there's sample disturbance has a lot of different tiers to it. Sampling basically mud rotary was one of them, making sure the drilling mud is on top, making sure the drilling mud density is controlled, and so that you collect the good samples. That's the first step, but you have to transport them properly, then you have to extrude them properly, and then you have, of course, the stress changes. So there's multiple tiers to this, and controlling some of these tiers can lead to good lab data that you can work with. At least if you wanna believe into the lab data, this is important. And especially if you're dealing with unique materials like coal ash, you could see depositions, variability in depositions, like you're seeing in this examples. This is an image from a source ash material, and what you're seeing here is two good ones that I kind of selected from good natural clays. But here's another one on the right with where you can see these failure pre-shear so-called plains, where this particular clay was very different due to its deposition. So if you want to capture some of these, if you want to know more about your material, this could help really design your lab testing. So some projects, I totally, as being a project manager, I totally understand you have certain time that you need to deliver the results, and you have a certain budget that you need to be within it. But at the end of the day, I think you save more time if you just spend the time in the beginning to really look for what you're going to do. How are you going to plan your lab testing, and which tubes are you going to test? And of course, their locations are also important. And this will help you down the road with the repeat tests and helping with the interpretation of the tests. So this is one of the important ones that could play a good role in interpreting lab data, especially with the soft materials and sensitive materials. Also with this unique materials where you can have really variable depositions. And also you can use the benefit of these measurements on the right to know that in the field you have a certain measurement of the tube, and in the X-ray you have a certain measurement of the tube. You can compare the two to see if the transportation is affected the materials. Also, you can check for the boundary effects. If the tube was, it was hard to push the tube, like you could see the band tubes in X-rays, that you don't want to use those in your lab testing. What we wrapped up is classification and consolidation. I wanted to stress again the importance of knowing the stress history of your materials. And you're seeing a typical output of a CRC test on the left, where you see the strain versus the effective stress. This is a typical summary curve for consolidation, where the pass pressure can be determined for this material. And what you're seeing on the bottom is the time rate, where if the settlement, total settlement and the time rate is important for the course of your project. So here is some interpretation where you could use different methods to come up with the pass pressure from a consolidation test. Here, the sigma prime V, sigma prime P is the maximum pass pressure that is important. Again, if it's the key input to how the material is going to behave relative to the in situ stresses versus where the pass pressure is. Here you're seeing a displacement square root of time chart, where you're seeing the primary consolidation and the secondary compression. And it's not, the secondary compression can become important in unique situations, again, where things can contribute to the total settlement, which we'll kind of touch on at the end with an example. But the trick here is the secondary compression may not be the C alpha value may not be the same all the time. So that's something that you may want to consider when you're doing your analysis. Some Strength testing that I want to touch on, very typical, is triaxial shear test, very widely done in the direct shear test to get a drain friction angle, which you do a more Coulomb type fitting here, as you're seeing a typical output of a triaxial and a direct shear here. If you're dealing with stability problems, you might want to do, and if you're dealing with undrained loading conditions, you might want to do an undrained test, which is a direct simple shear test, where you're seeing an undrained response here. Here is the shear stress with a shear strain, where you're seeing the axial strains are maintained within a certain distance, certain value to keep it constant volume test. This is a pseudo undrained test. And you have the pore pressure response, which is the typical for an undrained behavior here, which could be important if you're dealing with an undrained loading condition, and if you have a material who's going to behave this way. So it's again, planning for these tests, it is important, and based on what your goals are. And I want to touch on the cyclic direct simple shear test, and this is a post-cyclic phase. It looks like exactly the same output of a direct simple shear test, but it is done after earthquake cycling, after simulating an earthquake shaking with a certain parameters applied. But what I want to touch on here is the benefit of doing a companion testing on the same tube, ideally, to get an understanding of the percent reduction in your strength, because it's usually how we work with. It's one of the areas where it is hard to get the strength after the earthquake happens. So that's one of those that I want to stress. And resonant column testing is the other one, where you can determine the shear modulus and damping curves, and shear wave velocity testing. This is a advanced test that I don't really want to touch too much in detail. Some characterization that examples that I wanted to show. So I guess you got the message that I'm trying to give here. It's the combination of field and laboratory testing, and it's a good planning, and maybe changing the plan, making adjustments to your plans as you get more information, and use the benefit of the draft information that you're getting to kind of get all the data, all your data lined up to make some parameter development and interpretation of the data. So one of those that I wanted to show here is the stress history, like the consolidation tests that we talked about, where we determine the over-consolidation ratio, the maximum past pressure over to the in-situ stress. So this stress history is an important metric, and it can help understanding how your material is going to behave. It can also help if your sample quality is good or not. So here I'm showing an example from one of the sites that I worked, which I picked this one because I kind of wanted to show this. The consolidation test is not very typical to be typically done on sands, but particularly in this example, we were dealing with a silty sand material. It was classifying as sand-like because there are a lot of non-plastic locations, but where PI was variable, and it was to a certain extent plastic enough for us to sample. And we wanted to use the benefit of the consolidation test to understand if our data is going to make sense with the strength testing. So it was kind of good. I wanted to put this one out there. What you're seeing in the chart here is the CPT interpretation, bunch of CPTs pushed at the site, and the lab testing that was done along the profile where this particular one stood out with the quality of the sample, and the quality designation was D, which is kind of suggesting that another good quality sample. So consolidation tests can give you an idea about what to look and if you want what to look for in the strength tests, and can be really important to some of making sure your strength tests are reliable or not. So that's one of these examples that I wanted to show here, and can help you with understanding, managing the heterogeneity a little bit as well. The other example is comparing the field and the lab. Here, what I'm showing is through an ash deposit, and what you're seeing here is the unit weight stresses chart. Again, doing consolidation tests mostly in the clay-like materials was a good way of qualifying the samples for further lab testing. And a lot of unit weight tests were also used to kind of compare against the CPT interpretations, where the specific gravity is a key input, as I said, to these interpretations, especially going through the ash materials. And I also want to touch on the shear wave velocity measurements, the benefit of those as well, to see if you're here you're seeing some crossfall measurements through ash, and it might be a little bit small, but you're seeing red lab data as well compared against the field data. It's laboratory measurements are with the shear wave velocity are tricky. Sometimes you get good correlations, sometimes you don't. It really is not an easy process, but if you have good sources, if you have in-house people who can interpret the data, you can use the benefit of that to compare, and you can make some assessments that these samples are relatively representative of the field. The other metric one of the metrics that I want to show here is for the strength. So what we did here is, again, you're seeing a profile through ash, and these grays are again coal ash material. And what you're seeing is CPT interpretation of state parameter. So state parameter is another good metric, especially for sand-like materials, to understand how the pore pressure behavior is going to be for these materials, especially if you're dealing with seismic assessments and liquefaction type problems. But even there are short-term loading conditions without seismic, like construction conditions, you might want to benefit from the state parameter, where you're thinking how it is going to behave under loading. So what I want to point out here is the variability within a certain layer. So ideally, this full light gray layer is supposed to be the same ash that is deposited within the same time, where you can see the difference from the top to the bottom, how it changes in terms of state parameter. And these dash lines are kind of telling you to the right of it is behaving dilated, to the left of it behaving contracted. So you can see the variability, and that helped us to determine, okay, helps us determine to really, okay, maybe we need a different layer here, we need a different strength. And you can see on the right, the two tests that are conducted on these sublayers that are very different from each other in terms of undrained strength. So you get an unrealistically high undrained strength when the behavior is dilated, and you get more of a representative undrained behavior when the behavior is contracted. So that was kind of, I just want to point out, stress here is that you use your, if you don't process this and get an understanding of how the profile looks, you may want to be only signing this test, thinking that middle of the layer is going to represent the whole, and it may not be. So that's one of those examples. This is to kind of show that as an example. And one data here is to complement strength. What we're doing here is charting the undrained strength ratio to the CPT resistance, and this is CPT correlated on-drain strength based on case histories where slopes failure happened, Olson's relationship, so to speak, from Olson and Stark in 2003. That's what you're seeing in light gray. And we charted our data from all coal ash that we have. And you're kind of seeing the variability, which speaks to the variability of the ash. But you would be thinking that, these wide ranges of data and what do I do with this? But it was kind of eye-opening to see that the lab data, to a certain extent, agrees with the interpretations, even though they're like two separate independent ways of looking at it, and speaks to the variability of the material, but also it gives an understanding of these on-drain behaviors better than not knowing more, but just assuming things. So this was a good. We just need more data, of course. We need to get a better understanding if it's really correlating to the water contents, which are called out here. But long story short, I guess I wanted to say the relationships out there, if they are used properly with some knowledge and experience, they do a good job estimating some strengths. Another example to touch on a unique situation, if you have a seismic stability problem, where what I wanted to stress here is the monotonic response. And the monotonic response, the cyclic response, and the post-cyclic response. So this was a good test, a good set of tests that if you have the luxury of doing it, it's very valuable to get an understanding of the percent reduction in the strength. And very exactly which shear strains they are really acting on. So, and the benefit here is to really do these on the same tubes, on a good tube where you use the X-rays to really pick and choose where you do your tests. But that could be really beneficial to get a good understanding, relative understanding of the material. To touch on the stiffnesses, for unique materials like ash, what you're seeing on the left here is a typical chart as an input to a site response analysis. This is the shear modulus reduction chart. Here, what you see in the normalized shear modulus and then shear strain, where this is a key input to an amplification analysis, where you see the band and the range of materials, even though these are all ash materials. So there are good relationships out there that are part of the numerical modeling. But what's important here is, I guess, at the end of the day, the input to your modeling, it can be important. And if you're dealing with unique materials, you can use the benefit of lab testing to kind of calibrate. You see the dashed lines, the straight lines are kind of calibrated to the lab data to be entered into an amplification model. The recording will be available. So here are some good references that I really think they're very valuable. I'm going to skip to that quickly and just mention very briefly some of the case histories. I know I'm running a little late, but over the time, but let me just go through two quick cases and then we'll take some questions. So one of the cases is the slope stability case, where we looked at the seismic stability of a coal ash storage unit. But what I want to point out here is kind of what I talked about all day, all this hour today. So here is a stack where you see the upper portion of the stack and the lower portion of the stack. I just want to give you an idea about this, about where we're talking about. This is a coal ash stack. And here is that upper portion, and here is the dike that entails that, and then here is the lower portion in the pink, and there is a lower dike here, which we would call this upper dike, and this is lower dike. But this is a representative historical cross-section that before we went in there and analyzed it, this is looking at the historical information and thinking that there is residual clay under the dike, which would be our assumption and go to. But when we looked at same plan view, again, you're seeing this part is the upper portion of the stack. Here is the lower portion of the stack. When we overlay the historical information here, more like very old drawings, we see a valley of ash that could be potentially under the dike. And that's when we, since this is a seismic assessment and liquefaction is important, that's when we thought, okay, this is an important thing to figure out, and we tailored the this subsurface investigation based on that to see if really there is ash under the dike and how deep it is. And first we start with a CPT, as I said, so that's kind of what our kind of good practice of doing it. And we got a good CPT. The CPT is kind of confirming where the dike is, which pretty much where we expected it to be. But then we saw this low strength underlying material. But here CPT cannot really answer the question directly. So we wanted to, okay, we need to understand this because this could be clay with a soft clay lower strength. Because pore pressure behavior is high, low resistance. So we confirmed at least where we want to sample, right? And we kind of get the same lower blow counts. What we chose in our boring, in our companion boring, knowing that this is a lower strength material, let's just get tube samples as much as we can so we can test this material and understand its behavior. So, and do some classification testing on it. So where the two samples were collected and lab testing conducted, like we talked about, USCS classification test, and confirming that this is not a plastic material, and it was visually confirmed that it was an ash material, and that needed to be looked at in undrained behavior because it was under the water, and we needed to understand how it is going to behave. And we conducted a direct simple shear test to determine its potential undrained strength, which is you see a summary result on the right of that, which ended up being a truly undrained behavior. So we updated our models. Instead of being a clay, it is an ash material, and we totally changed this could be really affecting the stability of the stack. That is the concern here. So not only being, a different strength, it's also, since it's a seismic assessment, assuming it a clay, you would kind of disqualify it for liquefaction triggering analysis. So partly that's the other thing that you want to consider. You need to know the goal of the project and the loading conditions that you're working against. And definitely this ash was liquefying under the design earthquake. So this was the stability example, and I want to give a quick example for settlement. And this is on the fancy side of the world where you have a finite element model that you really model the tower. We're modeling a huge tower, which is putting a lot of stress on the clay. And we want to understand the settlement of this material. And here, there's two ways to this. You can use your FLAC models, and you have a lot of tools at hand. You have constitutive models that you're going to understand the initial stresses, but then you're going to determine the stresses beneath the tower. And okay, that's great. You do your analysis, you get the stresses for beneath the tower where the effect zone of influence is. Then here comes the importance of the lab testing, where you need, as we all know, this settlement is going to be dependent on if it's over consolidated or normal consolidated. You will have totally different coefficient of consolidations there. There, you really need to determine the pass pressure, where consolidation testing becomes very handy. And you go back to your model, enter that information. So this is the iterative process that I wanted to stress, the combination of the efforts, where the normally consolidated area versus the over-consolidated area is, and that will affect the settlement calculations. And not only that, the secondary compression is also, in this particular example, was very important. And knowing the difference of the change in the secondary compression, the C alpha coefficient, with the effect of being passing the pass pressure and being less than the pass pressure, it was really striking. As it was past the pass pressure, the rate was different, and this needed to be kind of entered into the finite element model in a more of a unique situation, and the constitutive model needed to be calibrated to really get the true behavior of the soil under the solver loading. So wanted to kind of put that out there as one of the unique examples that you wouldn't think that could affect the calculations. So I think with that, I'm being sorry for being a little bit over the time, but I guess my key takeaways is, as you can tell, it comes down. We could have all these very fancy tools. We have finite element models. We have stability models. Stability programs that we use it very quickly that can calculate all these substabilities. But it comes down to the input to these models. So what is the quality of the input parameters to these analyses is going to be the key. And if you're dealing with unique materials, if you're dealing with heterogeneous materials, you really need to pay attention and do a kind of a combined field and laboratory program that is requiring a lot of thinking up front to save time down the road. And at the end of the project, you're making a lot more educated interpretations of your soil properties. And I would like to take questions now, if we have some time.
All right. Yeah. So if anyone has any questions, please put them in the chat, and we'll get to them. I would like to thank Seda for going through all of that material. That was a lot. So great job there, and also for taking all the time putting this presentation together today. So please take a moment, think, and then put a question in the chat, and we'll get to it.